Okay, cool. So welcome back. Got the weekly announcements here. I've not quite finished grading. Oops, test two. I didn't mean to close that. Let me open that back up. Not finished grading test two. I'll get that done as soon as possible. About halfway done with that. Keep in mind that we don't have class on Wednesday. Wednesday is one of these wellness days that they're just thrown in there for all of our sanity or whatever. And so I know it says homework still due there, but since we're in the middle of what's going on right now, our homework this week is going to be due on Friday. And it's just one, quote unquote, just one assignment, but they're hard problems. It says 5 problems, but I think it's 8. Let me double check that real quick. Have it open. Thought I had it open. Let me see here. 2, 4, 6. Yeah, there's 8 problems. And we're getting into harder material like optimization, implicit differentiation, related rates. Those 3 topics are what we're getting into now. Are culmination of a lot of the things we've been working on. And so we've been building up to these things. And so they're tricky, is all I'm trying to say. So don't sleep on those homework problems. Don't wait to the last minute. We can look in some on Friday, but just be aware that those are challenging problems. And just be perfectly honest. Like I almost put another homework set due Friday and I was like, this one's enough. Okay, so that's where we are. No class Wednesday. I want to get back into the Wednesday homework things. I don't really like the Friday homework, and you probably don't either. But since we don't have class Wednesday, I'm just going to push it till Friday. But next week, I'd like to get back on the Wednesday train. And so let's try to do the homework for next Wednesday. And we should have no problem with that in terms of like when we cover that material. All right. Questions about anything? Thoughts about anything you want to look at? I'm assuming no one started the homework yet, which is fine. But if you have questions, let me know. If not, let's remember what we were doing. We're working on the optimization problems here, which is just finding maxes and mins, right? Just optimization just means we want the best, right? And so the best means if we have a function, it means the max. But also the best sometimes means the least as well. Like again, I always use the example of disease modeling, right? If you want to get the best out of a disease model, that usually means you want the disease to go down. And so optimization are doing those things. And, I wrote down these general steps that we should think about when we're working on these problems. Let me get this tool out. But we haven't used them yet. And so today is going to be the first day where we actually hone in on these steps, right? Because it says on the right here, sometimes you don't use these steps. And in the first couple examples we saw, we didn't use them. But we're going to use them moving forward, right? So let's just remind ourselves of the examples we already did. The reason we didn't use any of the steps because most of them had been done for us, right? We were given a function in this example, and we were asked, what is the max of it basically? What's the max cropped output? And so we found the max. And that's nothing that, is different than what you did on the test, for example. It was just taking a derivative, setting it equal to 0, right? That's how we find the max. And then we just classified it using the first derivative test. So, if you remember back, we looked at this back a week ago or last Wednesday, we sort of used this as a way to review for the test because we weren't doing anything different. We were just kind of finding the max with an application in mind, right? Same thing with the second example. But now we're moving into some problems that require us to think a little bit more carefully about what's going on and to follow the steps, like draw a picture, define variables, those kind of things. So let's read the question first. And I hope we can get excited about this because honestly, if you've been following along and the calculus seems okay, like we're ready to use it. Like this is cool stuff. We can actually do something real with it. So anyway, a farmer here. We've got a farmer. He's got a bunch of fencing, 300 or 3,000 feet of fencing, and he wants to create a pen, and he's going to put it next to a river so that he only has to make 3 of the walls, right? He's going to use like the river as one of the walls. And so he wants to use all the fence, and he wants the biggest fence. So what height and width would maximize the area? So let's slide back up to the steps here, and we'll do the first several things. Let's define the key variables, step 1. Okay, we'll do that. And then we will draw a picture. and then maybe we can come up with the objective function. Okay, so let's do those three things right away. So I'm going to start by drawing a picture just in case anyone's confused about what's going on here. It's like we have a river over here on one side, and this farmer wants to build a pen like this, right, with his 3,000 feet of fencing, and we're calling the height and the width of the pen would be the sides. For some reason in my notes I changed height to length, and I can't remember why. I don't think it really matters though. So the height we'll call h, and so let's let h equal, I guess height just feels like it sounds weird. I'm going to change it to length. I think that's probably why. I'm going to change the word height to length. So let's let L equal the length of the pen, and W will be the width. Doesn't really matter what we call them, right? But for some reason, I think height just feels like it's like off the ground to me for some reason. So let's label the sides. So we'll say W is the shorter side, and there's two of them, right? And then L will be the one that you only have one of, right? So we only have one of those sides because the river's on the other side. Okay. And the goal here is to find the biggest area, right? Maximize the area. And so our objective function then is to maximize the area. If you slide back up, objective function is the thing you're trying to optimize. And so we want the max area, right? That's the goal of the problem. And we know the formula for area. That's an easy formula. Oops, if I can spell area correct, that'd be good. So it's just length times width, right? And so this is our objective function. This is the thing we want to find the max of. We want to find the max of this, right? So that's the problem set up. Thoughts? This is a river over here. I don't know if that's clear. Kind of looked weird for a second. Now it's a river. Does that seem okay? We've done the first three steps, right? We drew a picture. Always helpful if it's not a simple problem where it's kind of given to us like the previous two up above. We want to draw a picture. It's usually helpful. We defined the variables. We wrote down the function we want to find the max of. Is that okay? Any questions about that setup so far? Let me open up the chat here. Okay. So, finding the max just means taking a derivative, finding critical points, like the things we know how to do, right? But in this function, there's two variables currently. There's an L and a W. And everything we've done so far only has one variable, usually X, for example, right? So we don't really know about like taking derivatives of two variables. How does that make sense? And so let's go back to the instructions here. And you can see that the next couple steps are to figure out if there's any constraints, which we do have. And then we use those constraints to write the objective function with just one variable. Because we currently have two, L and W. We wanted to just have one so we can take the derivative. Because then once we have that, we can just find the max using calculus, right? And just double check our answer, make sure it sounds reasonable. And so do you see what I'm saying here? We currently have two variables, but we're going to use our constraint to rewrite it in terms of just one. And so our constraint in this case is that we have 3,000 feet of fence. Oops, that's not what I wanted. And remember, let me just remind you what the constraints were in the last examples. Both the constraints in the previous examples up in the black right there, where we just wanted the variables to be positive. That was the only constraint we had. There was nothing big about that. And we also want the variables to be positive here, but we also have this added constraint of only having so much fence, right? So the constraints are, first, we need both L to be actually bigger than 0, right? We want to have a fence. If they equaled 0, we wouldn't have a fence. And so we want them to both be positive, actually. And we only have 3,000 feet of fence. And so ideally, we would want to use all of it, right? Why wouldn't we use all of it? And so we want the perimeter to equal 3,000. Right? That's a constraint. We want that thing to be big as possible, so long as when you add it all up, you get the materials we have. So this tells us our constraint. This tells us that when we add all the sides, and there's 2 W's, only 1 L, we need that to be 3,000, right? In other words, L plus 2W equals 3,000. And so this is like the constraint equation, you could call it. It's how we relate L and W. That's a W. Let me rewrite that so it's a little bit better looking. That's a W. And it's how we can take one of the variables out and replace it with the other one. Let me pause here and see if that looks okay. All right, so just to be clear, what we're about to do, we're going to solve for one variable. It doesn't matter which one. L is the easiest one to solve for, so I'm going to solve for L in terms of W. So that we can plug it into the formula, right? So just kind of looking ahead here. Well, let me just do it and then we'll look at it. So let's do that. So let's solve for L. Just subtract 2W to the other side. So we have L equals 3,000 minus 2W. And then we can take this and substitute it into the area formula above. Because then we'll only have W's in there. Right, so let's rewrite that. So let me switch colors here because we're kind of doing something different. Looks like my internet slowed down there for a second. I will pause. Could you hear me talking or was I cutting out there?
Couldn't hear you for like 5 seconds.
Oops, it looks like my volume's way down too. Hold on a second. Jimmy, repeat something there?
We couldn't hear you for like 5 seconds.
Okay, so what I was just saying is we just took the area equation that we started with up here. Right, we had this area formula, and so we're just rewriting it, but we're going to take out the L and we're going to put in that expression for L. And so what I had said was this is like a composition of functions thing, right? You're taking out the L and replacing it with a different function. So that ends up being this then, right? Here I am taking out the L, and then I'm going to put that expression right into it. And now it only has W's, right? And we can distribute the W through there and it becomes this. And this is a really easy thing to find the max of, right? This is the kind of thing that just takes one derivative, super easy to find the max of this. Right, but now it only has one variable was the point. It only has W's, not L's and W's. Like, what do you do there? If you want to take a derivative, what's the variable do you use? We don't know how to do that. But now there's only one variable. It's an easy power rule quadratic, easy to find the max. That's the hard part, I think, because at this point, I've been finished grading the test, so I don't know exactly how well people understand this. But if you understood the things on the last test, then you get how to find the max of this, and so that's not going to be the hard part. The hard part's setting up the problem, defining the variables, figuring out what we want to do, and then getting it to just have one variable. So this is the hard part. So I'd like to just pause here. I'm just going to kind of rifle off the answer here in a second, but I want to see if there are questions about this harder part. It's just going to be 3000W, I'm sorry, 3000 minus 4W, right? And we want that to be 0, right? We're just finding the critical points, and then we're finding the flat spots, and then we'll classify it. So we can pretty easily just add the 4W, divide by 4, and you would get W equals 750. Let's verify that it's actually a max. There's only one critical point, right? So if there are a bunch of critical points, we'd want to like test each one, figure out which is the biggest, etc. There's only one. So unless we did something wrong, it's the max. But let's just be sure, right? So let's verify it's a max. Let's verify W equals 750 is a max. I'm going to use the second derivative test. It doesn't really matter, but it's nice and easy in this case, because the second derivative is just a negative number, right? So this is always less than 0. Let me be more clear. If you tried to plug a number in there, it doesn't change that number. And so this is telling us 750 is a max, right? Because it's concave down.
I didn't really follow along there through that step. Can you repeat that?
Sure. So this implies it's concave down because the second derivative is negative. And we also know it's flat. So it's concave down because the second derivative negative is concave. It's flat because the first derivative is 0. And so that implies it's got to be a max.
How did you get -4? Where did that come from?
I took the derivative of the first derivative. So right, when you take the derivative of this piece, it becomes -4.
All right, gotcha.
Other thoughts? Trying to get the top thing to pop up again. Come on, pop up. Because I want to add another page. I hate when it does this. If I do that. If I do this. Okay. So just to kind of finish it, so the width, 750 is the biggest width. So what's the biggest length? Let's review the question actually. The question is, what's the biggest area, right? What height and width would maximize the area is what that says. So we have the width. Let's find the length. And so we just use the constraint again, right? So we know W is 750, and we know that L plus 2W is 3000. That was the constraint that we came up with. And so we can just plug the 750 in to get the L, right? And that's a feet measurement. And so we've answered the question. what dimensions maximize the area? It's L equals 1500 and W equals 750. If the question was, what is the biggest area? Then we would want to plug that into the area formula. And so let's just figure out what that is. Like if the question was, how big is the largest pen? Right, this is the difference between kind of thinking back to the material that was on the test. This is the difference between finding the location of where the max is, which is an X value, and then finding what the max is, right? Which you always take what you have and plug it back in. And so that's what this is doing. If you want to know the largest pen, we just plug it into the formula. Right, these are both feet measurements, and so when you multiply them together, you'll get square feet, which is an area formula or an area unit. I see this chat question that says, do we have to draw a picture? Do we really have to draw a picture every time? That's how I'm reading that one. If the picture is applicable, then yeah, I'd like to see a picture. It was not always applicable. The one we do next is not applicable. This is actually the only one I think that we'll look at that actually, a picture makes sense. I think, I honestly think it would be kind of hard to without, if you didn't have this picture here, to come up with this. I mean, maybe not like hard, like yes, it's doable to come up with that constraint without the picture. But when you have the picture, the constraint just follows from that. You just see like, oh yeah, I only have one L side. And I feel like if you didn't have the picture, you might miss that. So, is it the end of the world if you don't have a picture? No, but more than likely you're going to make a mistake if you don't draw the picture. So that's what I would say about that. I mean, if you look at the homework problems, the one where pictures are applicable, they always have a picture, and it's to help you with it, right? And you could kind of think about what it would look like if you didn't have one of those. Other thoughts? I didn't really mean that. Maybe that wasn't intended to be whiny. I wasn't really kidding. I was just kidding about that. Other thoughts? Clarification seems okay. I think there's one that's like this in the homework. It had something to do with fences. I was just looking through the homework to remind myself what was in there today. So follow along with this one. There's all similar to this one. So to check those out. And we can, my goal probably Friday is to, things telling me my internet's unstable. Can you hear me okay?
You're cutting out every so once in a while.
Okay. I don't know. My internet is so patchy lately. I've got an extender and everything. Anyway, I was just going to say my goal Friday is at least set up some of the more complicated problems. Like look at the picture, kind of do the objective function. Okay, let's do one that doesn't require a picture because those are so hard sometimes, pictures. Oof. So let's find two non-negative numbers whose sum is 9 that maximizes the product of one with the square of the other. So it's a super, it's like a very concise question. One sentence, easy kind of setup. It's, it's less interesting than the last one. At least the last one we were at least like building a fence or something. Now we're just finding some numbers. But it gives us another opportunity to use calculus in a similar kind of way. And there's one in the homework that's like this too. I happen to notice this morning as well. So we're thinking about, let's go to the list. We'll define the key variables. We can definitely do that. We don't need to draw a picture, right? There's not a picture that we would need to draw in terms of numbers. And let's figure out the objective function. So let's do those 3 things. So it looks like if we want to maximize the product means multiply. And we want to multiply the square of one with the other one, right? And so let's just define 2 numbers first. So n1 is a number. n2 is the other one. And we want to maximize, right? We want to maximize something, and we're going to maximize a product. So that's multiplication. And then we're going to square one of them is what that says. And so that's how we figure out the objective function. So we want to maximize something. What do we want to maximize? The product. So we're going to multiply something, and we're going to multiply one of them with the square of the other. That's what that's telling us to do. And that'll be our objective function. Let's call it Q. All right. Is that okay? Clarification about the setup so far. We did the first 3 steps. So we didn't have to draw anything, but we defined the numbers. We just wrote down the variables, and then we wrote down the objective function, right? So we want to maximize this thing. So find the max. But we first just needed to have one variable. Right? It has 2 variables right now. We need to do some kind of substitution to make it have just one. It's okay. Let's slide back up to the instructions real quick. So we did 1, 2, 3. We're going to then determine any constraints, and then we use those constraints to rewrite the function, and then we'll just find the max. Right, so that's the key thing. I think like 4 and 5 are usually the things that trip people up, which is relating the 2 variables and with the constraints, and then getting the substitution part. Those are things that oftentimes confuse people. So anyway, let me know if this doesn't look okay, right? So the constraints here, just one sentence, right? So what's the constraint? Oh yeah, their sum is 9. So that's the constraint. So their sum is 9. That implies n1 plus n2 has to be 9. And so we just solve for one, plug it into the other one. Doesn't really matter which one we do. You could solve for n1 and then plug it in that way, or you could solve for n2. It really doesn't matter. There's another constraint too, actually. I should have wrote that down before this one. What's the other constraint?
Non-negative numbers.
Yeah, non-negative. That's been a pretty typical one, right? And that's oftentimes the constraint in optimization problems is we want positive things. It doesn't really apply in this case, but it's nice that it's similar. So we also want n1 and n2 to be not negative. Just wanted to put that. I wish I put that first because it just kind of gets in the way over here, but that's okay. I'll just box it in. Right, but anyway, we want just one variable. So let's just solve for one in terms of the other one. And so n1 has to be 9 minus n2. Right? This is a nice thing that we can use to substitute into the above function. All right, and then it'll only have n2s in there. You with me? Let's do it. So we know Q equals n1 times n2 squared. Take this and plug it right in there, and you'll get this. Which becomes this. And now it only has n2s. And it's a cubic instead of a quadratic like the last one, but still not too bad to find the max. I gotta start writing smaller on this stuff. Just looking at my notes from my last class, I was really very easily able to fit this on a page. And now for some reason I just get so large on this iPad. Look at how big that was. It's enormous. Anyway, let's maximize this thing. Questions? This is the hard part. So, I mean, the hard part's over. So are there questions about that part? We're just going to find the max. All right, Q prime, nice easy power rule. It's just going to be 18n2 minus 3n2 squared. We want that to be 0 because we're trying to find the flat spots. It's a quadratic, so it's a little harder than the last one, but it's not too hard. You can use the quadratic formula if you really want to, or we can just factor out a 3n2. And then it becomes something that's not too bad. Right, we get 0 from this one. Or we get 6 from this one. Now this is one, well, yeah, this is one we have to be a little careful of. I guess, I don't know, we can probably reason through that 0 is not the answer, right? If we want to maximize the product of something and one of the things is 0, you're just going to end up with 0. So 0 is not going to be the answer. But it might be, I guess. And if we didn't sort of reason through that, we might think it's possible, right? And so this is one where we want to classify it. We want to be a little bit careful about classifying. It doesn't matter how you do it. I did the second derivative test last time, so maybe we should do the first derivative test on this one, just so we have some stuff to look at. Right, this is just from the last test, so let me know if this is a problem, but we're just going to test these things in the derivative, right? And we're going to test around 0, and so I'm going to test -1 and 1, and then we're going to test around 6, so I'm going to test 5 and 7. Right, so we get like -0, positive. And so this is a max, or a min, I mean. Right? And that makes sense. If you want the product to be as small as possible, make one of them 0, because then the product will be 0. But if you want it to be as big as possible, maybe 6 is the answer. And so let's look at that test. When we plug a 5 in, we get a positive number. When we plug a 7 in, we get a negative number. And so this is, right, increasing, flat, decreasing. This is telling us we have a max. What do you think? And did we answer the question? So the question is, find both the numbers that maximize this. So we found one of them. We can just find the other one by using the constraint again, right? We know we want them to add up to 9. And so if one of them's 6, the other one's got to be 3. And so we can kind of finish this off by saying we know n1 plus n2 is 9, and we know n2 is 6, and so that means n1 is 3. And if we want to know the max value, which is not the question, but sometimes the question might be, what is the maximum value? Then we just plug them into the formula again, right? So the max is n1 times n2 squared, which is going to be 3 times 6 squared, 18 times 36 is 108. So the biggest number you can get where you do n1 times n2 squared, where those two numbers add up to 9, is 108. Is that like earth-shattering? No, but hopefully you get the idea of how this can be useful, maybe more so with the fence question. I like these questions. These are good test type questions, to be perfectly honest with you. I haven't written the last test yet, but if I recall, the last time I did a test on this, I did one of these kind of problems because they're not super involved. You use the optimization thing, but you can just like do a one sentence kind of question without it being really complicated. Anyway, just a hint there. I don't, maybe I won't do that again, but there's a good chance I would say. Thoughts about the idea? What do you think?
Can you go up so I can see kind of how you did a little one of them, because I didn't really get that.
How far up? Here?
Okay, that's good. Thank you.
Can I clarify anything specifically? Go into details about, I don't know, any of it. Calculus, solving the algebra, anything there? All right. I am going to give you an opportunity to try the last one here. We're going to do it in breakout groups. So if you need to prepare yourself mentally for that, that's okay. Or if you're watching this video later, I would suggest you try this one yourself and then we'll look at the answer together. But this is another one of those problems where it's kind of set up for you. And I think the hard part about this one maybe is the algebra and solving the answer, just kind of thinking about some of the struggles people had with the homework last week. Solving problems like this can be tricky. And so this is a real world example. I took this one from a real paper that talked about, was it talking about cows again, I think, right? So it says, Charolais, Angus, and Hereford calves are types of cows, I believe. And so it talks about individual daily milk consumption for these three types of calves, and it's approximated by this function. And so the idea is like these t values are days. Right, isn't that right? It's weeks, actually. And so they're really young. They're between 1 and 26 weeks, so half a year old, between 0 and half a year old. As the milk consumption, right? So you plug in T in weeks and it tells you approximately how much one of these calves would drink in kilograms, it says. Excuse me. So we've got our two units, we've got kilograms and weeks, and we're going to do three things. We're going to, one, find the max, or find the age of the calf at which the max daily consumption occurs. So sometime during that period, maybe that kind of goes up and then they hit their max and then maybe they'll start drinking less. I don't know if it may not just keep going up, for example. The second question we're going to answer is how much milk is actually consumed. And the third part is just a conceptual question. Do we think that this is going to be the same value for all these calves, or, thinking about like how much do we trust these answers kind of thing, right? So sort of a no right or wrong answer to that one, just thinking about what we're doing and what the interpretation is. And so again, I'm going to break you up into groups and let you think about this one yourself a little bit. Let me just sort of set it up again a little bit further. So the first question, if we want to know where it occurs, we're going to take the derivative of m, set it equal to 0, and find the critical points, right? You'll find some critical points. Let me just remind myself. I think only one critical point comes out of here. Yeah, this one ends up being a little bit tricky, but we can do this. Oh yeah, this ends up looking tricky, but not actually being super tricky. So we're going to take a derivative, set it equal to 0. This is the part I want you to discuss, basically, is because the derivative is a product rule, and then solving it is a little bit tricky. And so you'll do that, and you'll get one critical point, t star. And then the second question is just plugging it into the function, right? How much milk is actually consumed is just going to be the function output at that critical point. And so I'd like to spend just a few minutes on this. Let's then say maybe 10 minutes, and then we'll go over the answer. And then we'll finish off. This is the last optimization page. So these are hopefully preparing you for the homework. We'll do a little bit more on Friday, but then we're going to move on and look at the next topic at the end of class today. Thoughts about anything before we think about that? All right, that's a product rule. This is a product rule because there's a t right here, and there's a t in the exponent. And so thinking about what the derivative is one of the things I'm trying to get you to do right now in these breakout rooms. All right, we'll just spend a few minutes on this. Call me in there if you need something. I'm going to, again, maybe 11:50, I'm going to call everyone back. I'm going to try to run through these breakout rooms. but let me know if I can clarify something. It'd be good if someone would take control and open up the whiteboard and at least get the derivative written down together and talk about how to solve it. That's what we're going for here. Okay, let's do that. All right, welcome back, folks. So I don't know how far you got in that. I was sensing I didn't make it around all the rooms, and I was sensing in the ones I did get to that there's some confusion in this one. So let's look at it together. So I've written down sort of the first part of the sort of this far, but know if this doesn't look okay. So it's a product rule, right? And so the t part, the t raised to the decimal, is just a power rule. It's a weird power rule, but it's a power rule. And so I'm writing down the power rule right here for that piece, right? Just bringing down the power, subtracting 1 off the power. You kind of ignore the 6.218 part. That's just a constant multiple, right? And then the right-hand piece is doing the derivative of the e to the x part, except it's a chain rule. And so you end up doing the derivative of the inside piece times the original exponential part. And together it's a product rule because you have the plus in the middle, right? F prime g plus fg prime. And so that's all I've written down here. And then I just, I multiplied 6 times 6.81 times 0.24 gives you the 1.52. And then I subtracted 1 off the power to get the minus 0.7 part. Let's see here, what else happened? Oh yeah, and then 0.28, those two things multiply to give you this piece. Anyway, most people I'd talked to, I think, had gotten this far. But are there questions about the derivative? This one's weird because of the decimals, obviously. But hopefully you can see what I'm saying there. Can I clarify something? Does that look all right? So then we want this to equal 0 because we're trying to find the max. And that's where I found that people were really confused. But are there questions? There's not questions about the derivative part? So think back to every other time we've had an exponential and we want it to be 0, right? We always factor that thing out. And that's the same thing that happens on this one. We factor out the exponential, and then we get something in the middle that we can set equal to 0. Oops. These decimals are throwing me through a loop, just rewriting them. Right? And every time we've done this, we always say, oh, well, exponentials are never 0, and so we don't get anything from that. And it's the same thing, right? So the exponential just kind of gets out of the way, and then we want this inside piece to equal 0, right? And so it's still tricky, though, because it looks like this, right? The t has a negative exponent, and so it's like, how am I going to solve this? And I agree, this totally looks funky. But when you just make one move, like a nice thing happens. So again, I got kind of caught up, but is there anyone who has an idea about how to solve that? What do we always do if we have we've got this t in the denominator? How do you get?
You have a 0 in the numerator.
I'm sorry, say that again. Oh, yeah, so you're talking about trying to solve a fraction. Yeah, so if we had something like a over b and we wanted that to be 0, we want the a to be 0. And that's true, but we don't have that situation because the t is in the denominator, actually, and there's nothing in the numerator that's a t. So I'm sort of thinking about, like, what if we had the problem 1 over x equals 6 or something? Like, how do you get variables out of denominators? That's the sort of technique I'm thinking about.
Cross multiply.
We could cross multiply, and we could actually, you're right, we could cross multiply on this one. Let's see, do we want to do that? Sure, let's go ahead and do that. It's a great idea. So let's add that thing to the other side so that we can cross multiply. All right, so 1.52 over this funky t thing equals 157 to the 0.242, and that's like over 1. And so if we cross multiplied, these two things multiply, and these two things multiply. Let me just slide that over so I can just do that right next to it. All right, so cross multiplying would end up being 1.52 times 1 equals 6 to the 0.758 to the point. I keep forgetting to write the 2. And this is like the answer, because when you add those exponents, because that's what you do in this situation, you add the exponents, right? It just equals, you get t, and you get t equals 1. I left my coefficient off though, I'm sorry. I forgot to rewrite the 0.157 part. All right, this had a coefficient 0.157. So we're almost there. So we have 1.52 equals 0.157 t to the, add those things. And those things happen at equal 1 when you add them together. All right, so we're like right at the end. Just divide by 0.157. And so we get t equals 1.52 over 0.157, which I think is 9.68. Remind myself what the questions are. So find the age at which the daily consumption, the max daily consumption is considered. So this is the day that it happens, right? Or the week, I guess, technically. The age. So this is the age at the max consumption. That's number 1. Question 2 was how much milk is consumed? And so if we want to know how much milk is consumed, just take that max day and plug it into the milk function, right? So just do m of 9.68. And I also did that ahead of time. Let me just remind myself what the function is. So this is, 6.28 times 9.68 to that weird variable, or I mean decimal. It's supposed to be a 2. Okay, this is messy because it's a real function. This actually approximates. Dairy farmers might be like using this function to figure out how much milk they need produced for their calves, for example. So yeah, it's not nice. You get these weird decimals. Right, so that ends up being approximately, let's see, what did I write down? About 8.5 kilograms. So when calves are about 9.5 weeks old, they will eat or drink 8.5 kilograms of milk a day. And that's a max. So they're kind of leading up to that day. So, if you're a farmer, a dairy farmer, at 10 weeks, you want to make sure you have your most milk available. And it'll be decreasing after that. I think I'm going to leave that one right there. Questions about optimization things? We've seen, 5 examples. 3 of them were just kind of like, quote unquote, normal max min problems. 2 of them were required a little more ingenuity. But hopefully you can kind of see how we can start using calculus to do interesting things, find meaningful values, right? Okay, what do you think?
I just have a quick question, Professor.
Yeah.
Since there was only one critical point, you don't need to classify it, right? Like the previous one with the 0 and the 6.
Yeah, I was sort of wondering if I should have done that. It's usually a good idea to. I was just kind of skipping over that one for the sake of time more than anything. If I had a little more time here, because I wanted to look at the next page, I might have just classified it for the sake of classification. But yeah, there's only one of them. So unless we did something funky, it's going to be the max.
Okay.
Yeah, thanks for clarifying that. Other things? Oh, what about the third question was, is this reasonable? Again, just for the sake of time, that's the sort of thing where it's like, well, Is every single calf going to drink that exact amount? No, right? It's an approximation. It's based on data, but some are going to want more or less than that. But this gives you an idea of how to prepare, is sort of what I was getting at there, right? Like, don't put all your eggs in the basket and say like, well, they only need this amount because they might need more, but it gives you an idea, right? That's the whole point of these math models, is like help you prepare, make projections, think about what's going to happen before it happens. But understanding that's not completely accurate is also important. Okay. Does that seem all right? I do just want to sort of talk about the next page. I think I do. I think I've got 15 minutes left. We don't have class Wednesday. I'd like to kind of fill up this time, and it's a one-page thing that is not too bad. So I'm gonna look at that unless there are questions. Happy to keep looking at this. Okay. The other thing I just want to look at today is this application of derivatives called the mean value theorem. And in my opinion, it's not the most important thing we do. Like, optimization is important. We're going to look at related rates. That stuff's like really highly applicable. This, I would file this in the category of an interesting thing that calculus tells us, and there's homework on it. And I may ask you a test question, but it's not the kind of thing that you like bring back necessarily to your major. I mean, there are some applications, but I don't know that I've like talked this topic down. Let's look at it. It's really not a bad topic. I just don't think it's as applicable as some of the other things. That's all. So what this says is, if we have a continuous function on some closed interval, excuse me, a comma b, then there must be some value between the endpoints. Notice how c is between a and b, right? So there's some value between the endpoints such that this happens, right? And this is sort of at the end of this rate of change question or section, because it's looking at the two types of rate of change we've seen before, right? This one on the right we know as the average rate of change. It's been a while since we've looked at that, maybe, but right, that was the first kind of rate of change we looked at. It was the slope formula. Remember that? So that's the average rate of change between the two function endpoints, right? And I'll draw a picture to remind you of that in a second. And then we use that to sort of, we took a derivative or a limit of that, and then we got the value on the left, right? And the value on the left, as a quick reminder, that's the instantaneous rate of change. At f of c. Or the way that we want to think about it in this context is the slope of the tangent line. Okay. And so what this is saying is, I'll say it a couple times and then we'll probably write the words down as well. But what it's saying is the average rate of change between the endpoints has to equal the instantaneous rate of change at somewhere between the endpoints. And a picture is a really good, helpful thing, I think, in this case to look at. And so let's do a couple pictures. Remind myself. Yeah. So I'm going to draw two graphs here. The first graph I'm going to draw is just going to kind of do this kind of thing. And let's say that A and B are here and here. And so what this graph or what this theorem is telling us is that here's f of A and here's f of B. And let's do the average rate of change between them, right? We know that that's just like a line that connects the two of them. So there I am putting that average rate of change down. I wanted that to be red. No, I actually wanted it to be purple. I wanted to match the thing up top there. And so what we're saying is, let me let everyone write that down first. It'd be helpful if you're looking at this. right? So the purple line there is representing the purple side, the average rate of change between f of a and f of b, right? Slope of the slope of that line. What this theorem is telling us is somewhere between the endpoints, the tangent line is going to be parallel to that one, right? In other words, the slope of the tangent line is the same as the slope of that line. And so if I just kind of, let me zoom in on this picture a little bit. If I think about slopes of tangent lines, if I'm over here, it's going to be too steep, right? If I'm over here, it's too flat. And so it's somewhere between those two things. I'm trying to think about something that is going to be perpendicular. Let me actually just go ahead and draw a perpendicular line. That might be a good idea. Perpendicular blue line. Let's try to make a parallel, excuse me, to that. Right? That looks like they're about the same, right? Same slope. Let me actually line them up, right? They look about the same. I can actually make them line up even better, probably, right? Let's make it just be a tangent line now. All right, so now it's a tangent line, and it looks like it touches at the point right here. So this would be our C. Right, and so C is between A and B, and the slope of the tangent line, which is in blue, is the same as the slope of the purple line, right? They're parallel to each other. And so that's what this theorem's telling us. It's just telling us between any 2 points, if you draw the average rate of change, somewhere between those 2 points, the instantaneous rate of change has got to be parallel. You get the same slope on those two things. And again, I'm trying to color code it here. So blue corresponds to the left-hand thing, and purple corresponds to the right. See what I'm saying there? I'm going to write this down in words in just a second, but is that okay? Shrink this up a little bit. So in words, it might be good to write this down in words. It tells us on a continuous interval. Continuous is key here, right? So it's got to be continuous. On a continuous interval a comma b, there is at least 1 point. I guess it's worth noticing that it could be more than 1 point. It's usually just one. So there's at least 1 point we call C, where the slope of the tangent line is the same as the average rate of change, right? Where the slope of the tangent line equals the average rate of change between the endpoints. It's always good to try to write this stuff out in just plain English, right? That's what this theorem's telling us. That's what the picture's showing us. The purple one's an average rate of change, the blue one's instantaneous, and they're parallel. Questions about that idea? I'm just trying to give you, it's always a good idea to understand what notation means in math. Like if we can just read what's inside the box there and have an idea of what it means, you're in great shape. You can be a mathematician. I really mean that, because that's the hardest thing about being a mathematician, is just reading the math and being able to kind of like draw a picture like this in your brain and saying, okay, yeah, I see what that means. Is it okay? So a specific application of this, the thing I want to draw on the right, is what's called Rolle's theorem. I don't know if we ever refer to that in here at all, but I was just reading this in the textbook recently. And Rolle's theorem tells us a specific application when the endpoints equal each other. Right? If we had the endpoints f of a equal f of b, then we get a 0 rate of change. Let's draw the picture and then we'll talk about it. So what if we had a graph that looked like this? And let's say our a and our b are on either sides of that hump. I want those to be like equal with each other. And so when we do an average rate of change between them, it's a horizontal line. right? The slope of that line is 0. Because I didn't draw the best picture, but we're assuming that they're equal with each other, right? And so there's some point in between A and B where the tangent line is also 0, the slope of the tangent line. What point would that be? At what point between A and B on this graph is the slope of the tangent line 0?
The max.
The max. Excellent, right? So without like doing any sort of work, I know that the blue part of this is going to be right at the max of that. Because I know that when you do at flat points, right, at peaks, the slope is 0. And so Rolle's theorem is just a specific application of this where it's saying, hey, if you have two endpoints and you have an average rate of trains, there must be a max or a min between the two of them. Just something to keep in mind. Again, not ground shattering, just kind of tying it back to where we started. This is where we started with derivatives, right? We started by looking at average rate of change, taking a limit, getting instantaneous rate of change, and now we're just sort of coming back to that and saying, now that we know everything there is to know about this, not really, but knowing a lot about this, we're kind of saying they're actually equal to each other some point on that interval. Okay, let's see here. There are a couple examples. I don't know if I want to do them now or if I want to wait till Friday. Kind of want to just do one of them. Is it really 212? I'm going to do at least one of them here. See how that goes. So the instructions on this first one might be, hey, see if we can even apply the theorem here. I forgot to write the instructions on, or I forgot to type them, so I'm just going to write them. Let's just check whether we can even apply the theorem. I'm going to represent mean value theorem as MVT to this situation. And so what we have is we have this rational function on the interval 0 to 2. And so let me just tell you the answer is that this function doesn't actually apply to this theorem, or the theorem doesn't apply to this function. Why do you think that is? What condition of this theorem is not being met by this function? What do you think? Right, the interval 0 to 2, and the denominator of this thing is x squared minus 1.
It's not continuous.
It's not continuous. Yeah, a couple people did. Nice job, Rory, as well. Right. So in order to apply the theorem, this is something that we always need to think about in a math class. Is if we want to use a theorem, we want to think, can I use it? And what this says is if we want to use this, we need to have a continuous function on the interval AB. And when we look at this problem, you can just look at the denominator and say, oh, wait a second. If x squared minus 1 is 0, i.e. x equals plus or minus 1, we get a discontinuity. And so this function does not apply, or this theorem does not apply to this function just because of that. And so I always like to just start with that one, because just pointing out you can't always use this theorem. And anytime we want to use something in math, the first question always is, can I? Do I meet the conditions? And so I just want to point out that since this particular function is not continuous on that entire interval, we can't apply this theorem. And I think there's a couple questions like that in the homework where it just says like, hey, can you apply this? If yes, go ahead and do it. And just pointing out that you always want to look at discontinuities to see if you can apply it in the first place. I am going to, I'm sorry, I'm going to do this last question. I just don't want to wait till Friday. I feel like if we wait till Friday, it'll be out of our brain. So I'm going to go a couple minutes over. If you really need to run out somewhere, I won't be offended, and this will be posted later, but I'm going to finish this one for continuity. So let's apply the mean value theorem to this function on this interval. So this is a polynomial now. And so we can apply it because it's continuous. Right? So let's do the same thought process. Are there any discontinuities? No, the function is a polynomial. It's continuous everywhere. And so the mean value theorem applies on that interval, but it just applies everywhere because it's a polynomial. Right? Let's go ahead and draw the picture too. Here's what f of x looks like. It's an x squared kind of thing. And I graphed it ahead of time and it kind of looked like this. That's what f of x looks like. And so we're looking between -2 and 2. And so -2 is over on the left side of the bottom there, and 2 is obviously over to the right. And so if we're looking at the average rate of change between those two functions, or excuse me, between those 2 points, it's going to be represented by this line. And so we can figure out the slope of that line, and then we can figure out where the corresponding parallel point happens. Right? So let's find the average rate of change on that interval. I was doing that in purple before. I will stick to that. So the average rate of change on the interval -2 to 2 is just given by that formula, right? F of 2 minus, excuse me, yeah, f of 2 minus f of -2 over 2 minus -2. Really easy to do. This is the kind of thing we did very early on in the course. Not very early on, but a little bit ago, right? We get 9 minus -3 over 4. So we get 12 divided by 4, which is 3. Right? So the slope of that line that we just found is 3. And so often these questions ask you, well, where is the corresponding C value? In other words, what point between -2 and 2 has a parallel line with that one? Parallel tangent line. And so that's what we're going to do in blue. So the question is, find where the derivative is 3, because we just found that we want it to be 3, right? Easy to do. Take a derivative, 2x plus 3, set it equal to 3. Very, very easy. And when we do that, we get 0, right? So what's going on there? So 2x equals 0, x equals 0. That's not an error. That's just telling us that the slope of the tangent line is parallel to the red one at 0. Right, so just to drive it home, what we just found is on the interval -2, 2, the instantaneous rate of change at 0 is the same as the average rate of change over that interval. Again, this isn't the kind of thing where it has a ton of meaning right now. It's just an interesting application that brings us back to where we started. Oh, did I make some joke, Josh? Get it? Continuity. I must have made some funny inadvertent thing. Maybe it was on purpose. I don't really remember what I said 5 minutes ago. But back to the picture here. The idea is like at 0 then, right? We found that this tangent line, and I drew a bad picture, so it's not going to look great. But that one is also going to have a slope of 3. That's what we just found. Should have drawn a better picture, but. And so there's a number of homework problems like this. They're due next week. I wasn't sure we would get to this today, which is why I made it due next week. And plus the ones in the homework on Friday, I think are particularly challenging. So it's fine to take a little more time with this one. But if you want to do these problems, you just look at the average rate of change and then set it equal to where you want the instantaneous rate of change to be. And then you can find the location. That's the way these problems usually work. Happy to look at some later in the week or next week. I apologize for going over a little bit, but thanks for your time. I'm happy to stick around if you've got some questions.
Thank you. Have a great day.
Have a great day.
Thank
Take
you.
care. Bye.
Thanks. Have a great day.